Hi everyone, my name is YUSOF, and today I'll be presenting a summary of my assignment titled Understanding Fluid Properties and Their Engineering Applications. This report focuses on how key fluids properties like viscosity, density, and surface tension affects engineering systems, especially in fluid flow and mixing processes. For introduction, why fluid properties matter? Fluid mechanics plays a critical role in chemical, mechanical, and process engineering. In particular, understanding fluid properties like viscosity, density, and surface tension is essential for optimizing industrial systems involving flow, mixing, and heat mass transfer. Where this report explores the definition and engineering significance of these properties, their impact on fluid behavior, and real-world applications. Fluid properties are critical in many industries, whether it's moving oil through a pipe or mixing chemicals in a reactor. Understanding how fluids behave helps engineers design systems that are safe, efficient, and cost-effective. So on our first property, viscosity is the resistance of a fluid to flow. Thick fluids like honey have higher viscosity, while water flows more easily. In mixing processes, high viscosity fluids require more energy and time, which affects designs and cost. And for my next property is density is the mass per unit volume. In mixing, particles with different densities may separate instead of mixing. Heavier particles have more momentum and behave differently, which engineers must account for when designing equipment. And last but not least, my last property, surface tension, is the force that holds liquid surfaces together. In mixing, it creates tiny bridges between particles. Breaking these bridges uses up energy, so stronger surface tension can slow down particle movements. So on our next slide, we have engineering applications of these fluid properties. So in viscosity impacts mixing time and energy usage, where you can see that higher viscosity differences makes mixing slower, and more energy is required to mix fluids with very different viscosities. And for our second one is densities. Particles may have the same size but different densities, basically meaning different masses. Mixing or segregation is influenced by momentum exchange, granular temperature differences. Heavy particles move more energetically, and this will lead to segregation during mixing. And for our last is surface tension. Surface tension causes liquid bridges form between particles in slightly wet systems. They are formed due to surface tension. Rupturing bridges consumes kinetic energy, and this slows particle motion and affects mixing rate. Basically, fixed rate at a very slow pace. And for my case study is the case study of how the fluid properties effect being shown on a flow regime map in a two-phase horizontal pipe flow. So, a study by Al Dogal and Gabby in 2021 investigated the effect of surface tension, viscosity, and density on flow regime maps in horizontal pipes. The study used a combination of experimental flow, maps, and pressure contours to visualize how fluid properties affect the transition boundaries between flow patterns like annular, slug, and plug flows. So we can say that in this case study, researchers explored how fluid properties affect two-phase flow in horizontal pipes. They found that density and viscosity strongly shifts flow patterns, while surface tension plays a smaller role. This helps engineers predict flow behavior and avoid pressure problems. And for our first fluid property is surface tension. As you can see on my left is case 1 0.02% surfactant, where it causes a weaker surface tension and promotes more wave formation. And the results in case 2, where the surfactant addition is up to 0.5%, causes a stronger surface tension, slows the transition, and delays flow regime changes. And for my second fluid property is viscosity, where the case 1 adds a 10% of glycerin that causes a lower viscosity support and faster transitions. Whereas case 2, 30% glycerin contributes to higher viscosity, leads to slower flow and more plugs and slug flow formation. And for my last fluid property is density, where as you can see on the left here, case 1, 25% calcium bromide is added that causes lower density, slightly affects the boundary shifts. And the results in case 2, where 75% calcium bromide is added, causes higher density, significantly impacts the inertial behavior and flow transition. So in conclusion of my presentation for today is that viscosity, density, and surface tension are more than just numbers. They shape how fluids behave. From industrial mixing to pipeline flow, understanding these properties helps engineers create better systems for our near future. These are the list of references that I have gathered and gained data and information from to show you how to understand how fluid properties works in mixing processes, and also the case study of how those three fluid properties are showcased on the flow region maps through an experimental of pipe flows. Thank you.